Now, in chapter 1, we just introduced measurements. Chapter 3 was about vectors. Chapters 2 and 4 to 9 was about translational motion. 10 and 11 were about rotation and how do they affect things. And 12 is going to be about what we call equilibrium. Now, in your book, it says equilibrium and elasticity, but elasticity is actually not part of this course at the moment. So we're going to focus on just sections 12.1 and 12.2, which are equilibrium. So let me share my screen. Okay. Equilibrium and elasticity. Now, we spoke about equilibrium back in chapter 8, if I'm not mistaken, when we were talking about, hills and dips and how do they affect each other. Okay. We said that, if something is at a hill, what happens? If something is at a dip, what happens? Can you see my screen, by the way?
No.
No? Why not? Okay, now you can see it. Okay. Now remember when we're talking about conservation of energy, total energy, potential energy, kinetic energy, we started about speaking about things that look like this, and we said if a ball is here, that it is in a stable equilibrium. If it goes here or here, it will come back to where it is. On the other hand, we said we have other types of equilibrium where we have something like this, where a tiny, tiny push would cause it to go all the way down. Remember this bit? So let's talk a little bit more about equilibrium and how it affects everything in today's life. Let's take an example of a football, okay? Either when it is resting or when it has a constant velocity. Notice constant velocity, not constant speed. So no change in direction and no change in speed. We call that an equilibrium, okay? What does an equilibrium mean? Why do we call this an equilibrium? Well, linear momentum is constant, it doesn't change. And angular momentum is also a constant, it doesn't change. So both types of momenta are constant. Take a look at this. You can use it as your background if you want. It's nice and smooth and soothing. Yeah. We can do things like these in real life where, it is barely balancing, but it is balanced. Yeah. It's very narrowly balanced. طشة هوا وبيطيح, but it is balanced nevertheless. Now, this is a balance where nothing is moving. Everything is stopped. And we call it static equilibrium, i.e., non-moving equilibrium. My linear momentum here is 0, and my angular momentum here is also 0. This is a photo from Jami'at Sultan Qaboos Al-Akbar. You have this really huge chandelier, and gravity is pulling it downwards. On the other hand, tension is pulling it upwards. But this thing is not moving either, right? It's not moving, it's just there. There are two forces on it, perfectly balanced, so there is no movement. It's still it's just happy to stay there. The first condition of equilibrium is the following. A body is in translational equilibrium if and only if the vector sum of all the external forces acting on it is 0. So F net equals 0, which means all the forces balance. It could have 100 forces on it, but as long as the ups and the downs and the lefts and the rights all balance, their net will be 0. So F net x 0, F net y 0, F net z 0. Now, in order for a force to be 0, the x components and y components must both be 0. Okay? And z component. So we can write it this way. F all the x's, sum 0, sum of all the fy's equals 0. Here's an example. On the top, this one, F up and F down are exactly the same. So what's my net force? 0. Down, I also have F up and F down, and they're also equal to 0. My F net is also equals to 0. But is it the same thing? Are these two equivalent? Are they? Are they not? Am I disconnected? Can you hear me? Okay. So you can hear me, just no one wants to answer. All right. Now, these two situations are not the same. Okay. In the top situation, the two forces balance and the thing would not move. In the bottom situation, although the forces balance, it will actually cause the bar to rotate around the center. This will cause it to rotate this way, and this will cause it to rotate this way. So they're not countering each other. It will start going in circles. We also need a torque net equals 0. Torque net x equals 0, torque net y equals to 0, and torque net z is equal to 0. So the vector sum of all the external forces that act on the body must be 0. The vector sum of all the external torques that act on the body, measured about any possible point, must also be 0. And the linear momentum of the body must be 0. Let's take an example of something like this. In the first photo, we have gravity down and Fn up at a tiny, tiny angle. In the second one, we have gravity down But Fn is not at the center, it's at the point of contact, so it's off center. And the third one, we have something perfectly at 90 degrees, and you have Fg absolutely down and Fn absolutely up. These three situations, also, although they both have Fg and Fn, and they're in opposite directions, are not equivalent. Let's try this out. A bar has 4 forces, all of the same magnitude exerted on it, as shown. What is the sign of the torque about the axis of rotation? Use the sign convention shown. So torque is 0, torque is positive, torque is negative. Just type your answer in the chat bar. You'll have, I'm giving you about a minute to do it. Okay, we have a whole bunch of B's. So this thing will cause it to go positive, 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 negative. The positives will win, so the torque is going to be positive, and this thing is going to rotate in this direction. Now we have something called the center of gravity. Okay. The gravitational force on a body effectively acts at one single point, called the center of gravity, or cog. Okay. Usually, that is at our center of mass. If gravitational acceleration is the same for all the elements of a body, then the body's center of gravity is coincident with the body's center of mass. Let's take an example. Talking about this chapter is easy. Doing the problems is a bit different. So where is this problem? Let me find it. 12-2. Okay. So in the figure shown, we have a uniform beam, meaning, the mass is the same left and right. Okay, the tiny mass in every piece is the same. A uniform beam of length L and mass m equals 1.8 kilograms is at rest on two scales. A uniform block with mass m equals 2.7 kilograms is at rest on the beam, with its center a distance L over 4 from the beam's left end. What do the scales read? Now, if we did not have this block, this would be a very silly question. These two scales would read exactly the same number. Okay, but now, and if we place this red block right in the center here, this question would also be silly. But now these scales are actually seeing something a little bit different. At this end, okay, it has Fn and Fg. Now, since this thing is not moving, it's just staying there, we conclude that it is at static equilibrium. Its linear momentum is 0. There is no torque, the net torque is 0, okay? And the net force is 0. We have gravity acting down the center. We have gravity acting on the red block at that side. We have the normal force on the first scale and the normal force on the right scale. Okay. This is what we have. Okay. Distances. FL is L over 2 away from the center and L over 4 away from the red block. Let's write down all the forces. FL plus FR, both up, minus capital Mg minus small mg, both down, is equal to 0. What about torque? Well, torque is R cross F, or RF sine theta. We have 0 distance. I'm going to look at torque about this point, about the left point. I can do it about the center or about the right, but I just choose to do it on the left side. So distance between FL and itself is 0. FL and mg is L over 4. FL and mg small, L over 2. And all the way to the other hand, on the other side, we have L plus FR. We have two equations. This gives me FR is equal to 15 newtons. On the other hand, FL is about 29 newtons once we plug the numbers in. If I'm looking at this would read 15 newtons, while this would read 29 newtons. Any questions so far? Okay, moving on. You decide to make yourself a desk. by attaching a wide shelf to the top of two legs. We're looking at a side view. When you put down a book on the end of the shelf, the force exerted on the shelf at the attachment point A is approximately what? Upwards, downwards, leftwards, rightwards, or zero? Okay, we have some people saying upwards, some people saying downwards. Now, since this is a desk, okay, I am assuming that we don't want it to move, right? Okay. When we put the book here, it's going to cause force downwards here. This is going to cause a clockwise torque, which, okay, would cause this to go upwards. But the question asked the force exerted on the shelf, not by the shelf. To stop it from moving, the leg will have to exert a force downwards so that there is no movement, so that your table doesn't flip over. Now, part B says, part B says, the force exerted on the shelf at the attachment point label B is what? At label B, the force can be upwards. There's no issue there. When we have a book on the right, this is what's going to happen, right? Now, to stop this from happening, because we don't want this to happen, yeah, this thing needs to bolt it down. And it needs an opposite force in the opposite direction. We don't want this to happen. We have a force down here. The table's leg needs to be stable enough, yeah, or bolted down enough to provide a downward force to stop this from happening. If it's not bolted, if it's lightweight, this is going to happen and your book is going to fall. In the middle here, at point B, yeah, you also have the shelf is doing upward. But if this is down and this is down and this is down, what happens if all the forces are down? If all these forces are down, then you have no forces counteracting them up. I'm talking about the net force at each, huh? The table is going to collapse. Now, since the table is not collapsing, that means we need to have a force here going higher up, going up. So that I'll call this F1, F2, oh no, let's call it FA, FB, FBook. So that we have FA plus FBook minus FB is equal to 0. And we have torque A plus torque book minus torque B is equal to 0. To remain at equilibrium, which is the whole point of having a table, I mean, it would be very weird if you have a table that's designed to throw things off it. These two equations need to be satisfied. And the only way for them to be satisfied is in this combination. Is if FA is down and FB supports it upwards. Consider this thing. You have something like a crane. It's called a boom crane. It's holding something upwards. Now this figure shows a safe hanging by a rope of negligible mass from a boom which has dimensions, height of 1.9 meters and width of 2.5 meters, which consists of a uniform hinged beam of mass 85 kilograms and a horizontal cable supporting it. This is something that we see in real life every single day. What is the tension on the cable? So we need to choose the type of cable. So we need to know what the tension on it is to choose the right type of cable. And what is the magnitude of the net force on the beam from the hinge? So we need to choose the right beam and the right cable. Otherwise, this thing is just going to drop and break. How do we do this? This is the information that we have. Mass 430 kilograms, mass 85 kg, cable, height 1.9, width 2.5, rope is negligible mass, cable is negligible mass. Hope you have all that written down. Let's take a look at all the forces that are taking place. We draw the beam, we have gravity pulling it downward, we have the mass of the safe pulling it from that direction, we have the tension of the cable pulling it left, and the hinge on the wall has also exerts a force, a horizontal force and a vertical force. Okay. So the net forces, if it's not moving, then the net forces and the net torques needs to be 0. Let's put down all the directions, all the dimensions. B over 2, and height A. First thing first, we don't want it to rotate. So let's have the torque equals to 0. Distance A multiplied by TC. TC will cause it to rotate this direction. Minus distance B times TR, which is going to make it rotate in this direction. Minus half BMG, which is also going to make it rotate in this direction, needs to be equal to 0. Is it clear how we ended up on this? Okay. Which tells us that TC, the only unknown in this equation is TC. We know A, B, TR, B, MG, we know all of them. The only unknown is TC. This gives us that the tension on the cable is about 6,100 newtons. So although the safe is only 430 kilograms in mass, which is about 400 newtons, give or take. Sorry, 4,000 newtons, give or take. 4,000, 4,200. The tension on the cable is more, it's 6,100 newtons. That's a lot. So what would the magnitude of the net force on the beam be? Well, these are the forces that we know. FGB is mg downwards, TR is mg downwards, TC is 6,100. We don't know the forces from the hinge. If we want Fnet x to be 0, then we will have FH minus TC is equal to 0. So FH is simply 6,100 also. And we want FV minus mg minus TR is equal to 0. So they have not rounded here. We need to round. Okay. So we have a horizontal force of 6,100 newtons, a vertical force of 5,047 newtons, and the magnitude is going to be 7,900 newtons. So in this image, this cable is withstanding about 6,100 newtons. And this beam is withstanding a magnitude, so the force are like this and like this, so a magnitude of about 8,000 newtons, give or take. Okay, it's quite difficult to get these cranes to work. That is why the next time you look at a crane, you're driving around and you see a crane, look at it. You will see that it is placed on the ground with a solid foundation. Then you have this thing. Then you have the crane like this, with, It's holding onto things from here. But then here you will find something very, very large at the end here. A very, very large block weighing many, many tons. And the reason for that is because of this calculation. Whenever you are getting something up here, this thing needs to balance the torque and the forces. One more sample problem. 12.03. Okay. This is the question text. In this figure, a ladder of length L equals 12 meters and mass M equals 45 kilograms. There we go. A ladder of length L equals 12 meters and mass M equals 45 kilograms leans against a slick wall so that there's no friction between the ladder and the wall. The ladder's upper end is at height h equals 9.3 meters from the ground. The lower end is fixed. There's support here, okay? But there's no support here, but there is support down here. The ladder's center of mass is L/3 from the lower end. So, and here. Along the length of the ladder. A firefighter of mass 72 kilograms climbs the ladder until her center of mass is L/2 from the lower end. At this point, what are the magnitudes of the forces on the ladder from the wall and from the pavement? Here's our ladder. We have F wall pushing on it from up. We have mg for the person, mg for the wall. On the ground, we have py and px. Now you might ask, okay, if on the ground we have py and px, on the top, why do we only have fw in that direction? Why don't we have fw here also? The reason is because it's frictionless, we don't have any forces in that direction. Okay, the ladder is pushing on the wall in that direction, so the wall is pushing it back in this direction. There's nothing happening on the y-axis. Well, height is 9.3. We have all of these distances. We have all of these distances. First thing first, let's make sure torque is 0. We do not want the ladder to rotate while there is a person on it. So, minus h Fw plus A/2 mg plus A/3 small mg plus 0 px. So I'm taking my pivoting point to be here at the bottom. Plus 0 py is equal to 0. Could I have taken this rotating point about the middle? Yes. Could I have taken it about the end? Yes. Why did I take it about the bottom? Because I have two forces on the bottom, and if I take the pivoting point at the bottom, they will both be multiplied by 0, and I'm going to get rid of them. What is A? I keep saying A. Well, I know this distance, and I know this distance. This is 9.3. This is length. So my A is going to be using Pythagoras. The only unknown in that equation is FW. So FW is about 410 newtons. We do again the net of the forces. In the x-axis, FW minus FPX is equal to 0. In the y direction, FPY minus the 2 mg's is equal to 0. And so we have FPY is about 1,100 newtons. Now, when you are designing a ladder, for example, whether for home use, or for commercial use, for the firefighters, for whatever, you need to choose your metals, you need to choose your materials in a specific way to be able to handle these kinds of forces. Otherwise, you have an emergency situation, a guy starts going up and halfway the ladder slips or drops or breaks or something happens, which is, well, you don't want that to happen. Okay. So that is that for now, for today's lecture. Any questions? No?
No, Doctor, thank you.
Okay, so we can call it a day. And I'll see you, inshallah, next week. Have a great day.